Imagine your windows doing more than just, letting light in. What if they could actually power your home
Right.
and maybe even change their tint automatically to block the sun's glare?
That's the idea. It sounds like something out of science fiction, doesn't it?
It really does. But it's not anymore. That's the revolutionary promise of smart windows. And today, we're doing a deep dive into the cutting-edge science, making it real.
Yeah, and our mission here is to really unpack the journey of these perovskite materials. They're a game-changing family of crystals, fundamentally altering how buildings interact with sunlight.
So we're going to look at how they're engineered into these smart windows that can intelligently darken with heat and generate electricity at the same time.
Exactly. We want you to understand the ingenious solutions researchers are developing to bring these, well, frankly, futuristic windows into everyday life.
And to guide us, we've got insights from three really interesting sources.
That's right. We'll kick off with a look at some early innovations, drawing from Science magazine. Then we'll jump to an update from Ike's Spectrum on where things stand with commercialization efforts.
Okay.
And finally, we'll dig into a groundbreaking paper from Nature Communications. It details a new fabrication method that's unlocking some incredible levels of performance and, interestingly, aesthetics, too.
Aesthetics, right. So get ready to see how your windows could soon be part of the solution for energy efficiency and maybe even building design itself.
Definitely.
So thinking back, before perovskites came along, what were the first attempts at smart windows? What were their big limitations?
Well, traditional windows are just simple panes of glass letting light through. Pretty basic.
Sure.
The first real stabs at making them smart were these electrochromic windows. You might have seen them on the Boeing 787 Dreamliner.
Oh yeah, the dimmable ones. Push a button, the window darkens. Seemed pretty futuristic back then.
Totally. They could switch between transparent and opaque, which was innovative.
But our sources flag some pretty big drawbacks, right? Why didn't they take over, especially in buildings?
Exactly. While they were cool tech, they had a critical flaw for widespread use in buildings. They needed an outside power source just to darken.
Ah, okay.
Plus, they were more expensive and sometimes a bit inconsistent in how well they actually blocked the light. So, yeah, all those factors really prevented them from making a big splash in the larger building market.
Right. Which kind of sets the stage for perovskites.
Precisely. This is where perovskites really sparked a revolution.
So what is it about these materials, this new class of crystals? What let them overcome those earlier limitations?
Well, perovskites are this family of crystalline materials that offered a whole new path. They could combine that smart window function, changing transparency based on temperature, with solar energy harvesting, all in one.
Okay, that's the key difference, doing both.
Yes, and a huge part of the story is their efficiency. Perovskite solar cells are getting incredibly good, nearly matching top-tier silicon panels. We're talking over 22% sunlight to electricity conversion for the best perovskites versus maybe 25% for silicon.
Wow, that close already.
Yeah, and here's the kicker. The raw materials for perovskites are way cheaper.
Right, that's a massive advantage.
It really is.
Yeah.
This near parity in efficiency, combined with the lower cost, makes them a serious contender. It's not just some niche thing. It could genuinely challenge silicon's dominance and make integrating solar much more accessible.
So cheaper and almost as efficient. Okay, so our sources mentioned the first big step in combining these functions came around November 2017. What did that first sort of combined perovskite solar window actually look like?
Yeah, that was a lead-based perovskite window. Its trick was switching from transparent to opaque when it hit about 60 degrees Celsius.
Okay, how did it do that?
The mechanism was pretty clever, actually. At cooler temperatures, the perovskite material formed a complex structure with methylamine.
Methylamine, okay.
When things warmed up, the methylamine basically vaporized and broke away from the structure. That change caused the window to darken and start absorbing sunlight.
And then it could reverse.
Yep. When the heat dissipated, say, the sun goes down, the methylamine would move back into the structure and boom, transparent again.
And it generated power too.
It did. When it was in that warm, opaque state, it could convert up to 11.3% of the sun's energy, hitting it into electricity.
11%, that's not bad for a first attempt.
Oh.
Sounds promising. But like with many early breakthroughs, there are usually some catches.
You guessed it. There was a major drawback.
Uh-huh.
The efficiency dropped off quite significantly after just a few switching cycles. back and forth a few times, and it wasn't working nearly as well.
Why was that happening?
The likely culprit was that methylamine. It seems it wasn't fully returning the perovskite to its original perfect crystalline arrangement each time it cooled down, so you got degradation.
I see. So that instability really killed the long-term potential of that specific design.
Exactly. And that setback really lit a fire under researchers to find a different recipe, a different formulation for these perovskite materials that could offer long-term stability.
Right, the hunt was on. And that hunt led to a pretty significant stability breakthrough from Pudong Yang's team at UC Berkeley. What did they do differently?
Their big innovation was developing a cesium-based perovskite solar window. It still turned opaque and produced electricity when heated, but the crucial part was no methylamine.
Oh, they got rid of the weak link.
Pretty much. This directly tackled that stability problem. It allowed the window to switch back and forth repeatedly without that performance drop-off.
Okay, progress. But were there still downsides?
Oh, definitely. It wasn't perfect yet. For one, the initial versions needed to get quite hot, over 100 degrees Celsius, to make the switch.
Oof, that's pretty hot for a window.
Yeah, not ideal. And the efficiency was lower, only around 7% initially. Plus, there was an aesthetic issue. One expert called it a crucial factor for builders.
Let me guess, it wasn't perfectly clear.
Worse, it had a distinct reddish tint when it was opaque.
Oh, yeah, I can see architects not loving that. A red window.
Exactly. So still hurdles to overcome. But the good news is Yang's team was already working on it. They apparently have a variation in development that switches at a much more reasonable 50 to 60 degrees Celsius.
Okay, that's more like it.
They just need to get the efficiency back up on that version. So yeah, the hunt for the perfect perovskite definitely continues.
It sounds like a classic science story. Solve one problem, uncover another.
Absolutely.
Yeah.
And this quest for better materials ties directly into this really exciting concept called building integrated photovoltaics, or BIPV.
BIPV, right. So not just panels on the building, but part of the building.
Precisely. Companies like Panasonic are envisioning these semi-transparent perovskite panels that aren't just stuck on the roof. They could actually be the building facade, the walls, even the windows themselves, generating electricity right there on site.
And they're actually testing this already.
They are. Our sources say that back in August 2023, Panasonic started testing a prototype. They use them as glass balustrade panels, on a balcony, nearly a meter high, 4 meters wide, on a model house in Japan.
Wow. Okay. So real-world testing. And they can even customize how transparent they are. How does that work with the solar material? Isn't it usually opaque?
That's one of the unique things about perovskites compared to, say, silicon.
Hmm.
Silicon solar cells absorb pretty much all visible light, which is why they look black or dark blue.
Right.
Perovskites, however, typically have what's called a wider band gap, usually over 1.5 electron volts. This means they naturally let some light through, particularly the red part of the spectrum. So they have this inherent semi-transparency.
So they start out somewhat see-through.
Exactly. And during fabrication, Panasonic can tweak things to control just how transparent they are. But there's a trade-off you need to understand.
Always a trade-off. Let me guess. Transparency versus efficiency.
You got it. It's basically a linear relationship. If you have a panel that could be 20% efficient if it were opaque, but you decide you need it to be 50% transparent,
Then the efficiency drops.
right down to about 10%. So
Yeah.
you're constantly balancing how much light you want to let through versus how much electricity you want to generate.
Makes sense.
Yeah.
But, okay, if these are going to be part of the building, durability is massive. Our sources mention perovskites can be vulnerable. They tend to break down when exposed to heat, moisture, snow.
Yeah, basically everything a building facade faces every single day. It's a huge challenge.
So how is Panasonic tackling that problem?
They've got a really smart two-pronged approach. First, on the material science side, they've worked on making the perovskite itself more robust. They do this by doping it, basically adding tiny amounts of other atoms, like cesium and rubidium.
Okay, strengthening the core material.
Exactly. That gave them much higher thermal stability, and they reported hitting 20.8% efficiency with that doped material back in January 2019.
That's impressive. What's the second prong?
That's on the architectural side. They figured, okay, let's protect this sensitive material. So they encase the perovskite layer within completely sealed architectural double glass.
Like a standard insulated window unit?
Kind of, yeah.
Huh.
It provides rigidity, sure, but crucially, it seals the perovskite off from moisture and air. It's like creating a little controlled microenvironment for the perovskite layer inside the glass sandwich.
That's clever. Protect the material and make it structurally sound.
Right. Essential for long-term use in a building.
Okay, so they have a more stable material and they're protecting it well. But what about actually making these things precisely? Our sources talk about challenges with traditional methods for patterning the tiny solar cells, the microcells. They apparently led to defects.
Yeah, that was a big issue. Traditional methods could cause problems like deformed shapes, little voids or gaps in the material, and that, of course, hurt the efficiency. You need these layers to be perfect.
So how do they crack that problem?
This is where things get really innovative. There was a breakthrough paper in Nature Communications in April 2022 describing a new process. It's called swelling-induced crack propagation.
Swelling induced. Okay, that sounds interesting. How does it work?
It's a type of lift-off patterning. So imagine you start by putting down patterned layers of polymers on your base. Then you spin coat the perovskite film over that pattern.
Correct.
Then comes the clever part. You introduce something called an anti-solvent. It does two things. It dissolves one of the polymer layers, and it causes another specific polymer layer, polyamide, to gently swell.
Ah, so the swelling does the work.
Exactly.
Yeah.
But it's very controlled, slow swelling. As the polyamide swells, it applies a very precise mechanical stress right along the edges of the pattern. This stress forms and guides tiny cracks.
So it cracks the perovskite film, but in a good way.
Precisely where you want it to crack. Along the pattern lines. This allows the pattern sections of the perovskite film to be lifted off cleanly, without creating fractures or leaving bits behind. You end up with these really flat, uniform, highly crystalline microcells.
Wow, that's incredibly precise control, almost like nanoscale engineering.
It really is. And here's another key benefit. This method allows for what they call simultaneous lift-off patterning. You can pattern both the perovskite layer and the layer right next to it, the electron transport layer, or ETL, at the same time.
Why is that important?
The ETL is crucial. It's where the electrical charges generated by the light actually move out of the perovskite. By patterning them together perfectly, you significantly reduce defects right at that interface, that critical boundary between the layers. Fewer defects means fewer places for those charge carriers to get stuck or lost.
Which boosts efficiency.
Big time. It's key for getting the most power out.
That is seriously clever manufacturing. And the results, the performance numbers.
Pretty remarkable. Microcells made this way hit a power conversion efficiency, PCE, of 20.1%.
20%.
Yeah, which was nearly identical to what they got from unpatterned, basically perfect lab samples. And they showed a stabilized power output of 19.9%. That means it wasn't just a peak, it could sustain that level.
And crucially, could they scale it? Make lots of these microcells?
Yes. They showed that the efficiency stayed stable even when they dramatically increased the number of microcells in a given area, going from about 114 up to over 800.
That's huge. It proves the process is consistent and potentially scalable for real manufacturing.
Exactly. It's a big step toward commercial viability.
Okay, so we have efficient, stable, manufacturable cells. But we talked about aesthetics earlier. The goal is a window, right? Something you look through.
Right. It can't just be about power. It has to look good and function as a window. So researchers looked at how small these microcells needed to be.
To be invisible, basically.
Pretty much. Turns out, the human eye's angular resolution, how small a detail you can see, is about 120 micrometers at a normal viewing distance, say 40 centimeters.
Okay.
And they found they can make these perovskite microcells as small as 100 micrometers.
So smaller than the limit of what we can resolve, you wouldn't even see them.
Correct. You get this visually uniform window surface. They also noted you don't want to go too small, though. Below about 50 micrometers, you can start getting increased haze because the tiny structures scatter light more.
Ah, okay, so there's a sweet spot for size. 100 microns sounds ideal.
Seems to be. And to optimize things even further, both transparency and light absorption, they added something called moth-eye nanostructures.
Moth-eye, like inspired by actual moths.
Exactly. Moth-eyes have these amazing nanostructures that minimize reflection and maximize light absorption. Researchers basically mimic that design on the top and bottom surfaces of these semi-transparent panels.
That's brilliant bio-inspiration. What benefits do these moth-eye structures provide?
Several. They improve the overall light transmittance, let more light through by about 10%. They also enhance the chromatic properties, things like the hue, saturation, brightness. And they help the panel absorb light more effectively across a wider range of angles.
So better light, better color, better power generation, especially when the sun isn't hitting it straight on.
You got it. It's a neat trick borrowed from nature.
So when we talk performance for these semi-transparent windows, what are the key metrics? Our sources mention LUE.
Right, light utilization efficiency, LUE. It's a really important metric because it combines both how much light gets through and how much power is generated. It's calculated by multiplying the average visible transmittance, or AVT,
How much visible light passes through?
but power conversion efficiency, PCE. So it balances light and power.
Okay. And they also mentioned CRI.
Yes, color rendering index.
Yeah.
That measures how accurately colors appear when you look through the window. You want a high CRI, ideally above 90%, so things don't look weirdly tinted.
Right, you want the view outside to look natural. So what kind of numbers did they achieve with these optimized panels, the ones with the moth-eye structures?
The results are really impressive. They achieved an LUE of 4.67.
And how does that stack up?
Well, that came from having an average visible transmittance, AVT, of about 56.45%, so over half the visible light gets through, and a PCE of about 8.28%.
Okay.
And the CRI was fantastic, around 97.5%.
Wow, 97.5. That's excellent color rendering.
It is, and that overall LUE of 4.67 significantly surpasses what's often considered the target for an ideal solar window, which is usually an AVT over 50% and an LUE over 2.5. So they're really hitting a great balance of transparency, power, and color fidelity.
That really does sound like a window that works, but it gets even cooler, right? These windows don't just have to be clear, they can be colorful.
Yes, this is another fascinating development. Researchers figured out how to add specific colors using what are called metal insulator metal, or MIM structures.
MIM structures. Okay, how do they create color?
These MIM layers are added, usually to the backside, and they create resonant structures. Think of them like tiny filters that only allow specific wavelengths, specific colors of light to pass through or reflect. The exact color depends on the thickness of that middle insulator layer.
So you can tune the color by tuning the thickness. Red, blue, green.
Exactly. But here's the really clever part. Even though they're adding these color layers, the power conversion efficiency of the window remains almost constant, regardless of the color being displayed.
Wait, really? Adding color doesn't hurt the power generation. How?
Because the MIM structure is typically applied to the backside and primarily affects the areas between the active perovskite microcells. It's managing the light in the non-generating parts so it doesn't really interfere with the light hitting the perovskite itself.
That is a huge win for design integration. Architects would love that. Our sources even say they demonstrated a mosaic patterned window.
Yeah, they made one with sections of red, green, blue, and purple. Like stained glass, but it generates power. And those moth-eye nanostructures we talked about, they actually help make these colored sections appear even brighter and more vivid.
So you could have a window that's a piece of art, customized with colors, and it's still an efficient power generator. That's amazing.
It really opens up possibilities.
So looking ahead, where does this technology stand in terms of actually reaching the market? What's Panasonic's plan?
Well, they're moving forward quite deliberately. Panasonic is planning to start a pilot production line. We're talking 1 meter by 1.8 meter panels starting in April of next year, so 2026.
Okay, pilot line next year.
And they have plans to scale that up later to make even larger panels, like 1.8 by 4 meters. Their goal, according to the sources, is to actually commercialize these BIPV products within about 5 years.
5 years, so by around 2028, 2029, that's pretty soon, relatively speaking.
It is an ambitious timeline. Yeah. And they're aiming for an energy conversion rate close to that 20% mark we discussed earlier.
And what's their strategy for the market? Are they going head-to-head with standard solar panels?
Interestingly, no. Their plan seems to be less about competing on standard-sized commodity panels and more about focusing on customization.
Ah, leveraging that BIPV concept.
Exactly. They have this flexible inkjet production method, which allows them to tailor the panel's size, transparency, maybe even color, to meet the specific requirements of different buildings and architectural designs.
That makes a lot of sense. Focus on the niche where this technology offers something unique.
Right. So if you zoom out, what does all this mean? It's more than just another way to generate electricity.
Yeah, it feels bigger than that.
It's a huge step for that whole building integrated photovoltaics market. We're talking about solutions that can generate power, yes, but also block heat, which could reduce air conditioning demand significantly.
Big energy savings there.
Absolutely. And doing all this while potentially looking really good, blending seamlessly into the building's design, or even enhancing it with color. It's combining high performance with aesthetics.
So what this really means for you, listening, is that you might soon live or work in buildings where the walls, the windows, the very surfaces around you are actively working, generating energy, controlling climate.
All while looking stylish and letting in natural light. It's a fundamental shift in how we think about buildings and energy.
So just to recap, we've really unpacked how these perovskite materials are driving a revolution, turning static windows into these dynamic, energy-producing surfaces.
Yeah, we saw how they overcame the hurdles of those early smart glass attempts, the stability issues,
Right, the methylamine problem.
and developed these incredibly clever fabrication methods like that swelling-induced crack propagation to get high performance and precision.
And even figured out how to add vibrant colors without sacrificing efficiency. The whole journey is just, well, fascinating.
What really stands out, I think, is how scientists aren't just making incremental improvements here. They're fundamentally reimagining how our built environment itself can be an active part of our energy future.
That's the real aha moment, isn't it? It's not just a better window, it's a different kind of building skin.
Exactly.
Which leads to a final thought to leave you with. If the very skin of our buildings can become an active energy producer and climate controller, how might that redefine not just architecture, but entire urban landscapes and even our whole relationship with energy consumption in the coming decade?